Hello, I'm Candace Rulo, Managing Editor of Manufacturing Engineering magazine, and this is another SME Media webinar. Our topic is Advanced Simulation to Leverage True Additive Manufacturing Potential. This presentation is sponsored by MSC Software. MSC Software develops simulation software technology that enables engineers to validate and optimize their designs using virtual prototypes. As a trusted partner, MSC Software helps companies improve quality, save time, and reduce costs associated with design and test of manufactured products. MSC Software products accurately and reliably predict how products will behave in the real world to help engineers design more innovative products quickly and cost-effectively. Today's webinar is about using advanced simulation to leverage true additive manufacturing potential. Our presenters today are Olivier Latier and Jeff Robertson of Business Development for Additive Manufacturing at MSC Software. With more than 30,000 additively manufactured parts a year going into production aircraft, trains, and automobiles, additive manufacturing has now become an effective industrial production technique. While AM brings valuable opportunities to the industry, it still faces the same challenges and other manufacturing processes face to meet high requirement applications. These challenges call for advanced customized simulation techniques to optimize the design to print workflow and determine the optimal process flow much faster and at a dramatically lower cost. During this webinar, Olivier and Jeff will discuss how to replace the expensive physical trial and error process with a holistic simulation approach. Furthermore, they will explore the simulation capabilities and the applications they apply to both metals and polymers. Before I turn things over to Olivier and Jeff, I'd like to outline how the webinar will proceed and a couple housekeeping items. On the right side of the screen, you'll find a question and answer box. If at any time during the presentation you'd like to ask a question, please type it in the box and send it along. These questions will be answered at the end of the presentation. Should we run out of time, the questions will be sent to Olivier and Jeff and you'll receive an answer via email. Should you experience any difficulty during the webinar, such as a blank screen or a lack of sound, please use the Q&A box to alert us, and we will respond individually in writing with a suggested fix. That brings us to the final housekeeping item. Should you experience a difficulty such as this, the presentation will be available in recorded form at about 4 p.m. Eastern Time today. You may then watch the recorded version of this webinar at any time and place when you have more bandwidth. You may also watch the webinar as many times as you wish to catch details you might have missed or for any other reason. All you must do is sign in again using the credentials you used to join us now. You may even share those credentials with colleagues who might benefit from learning more about this topic. Now let me turn the microphone over to Olivier and Jeff, who will both introduce you to using additive simulation to leverage true additive manufacturing potential. Olivier and Jeff, the floor is yours.
All right, thank you. You mentioned my name is Jeff Robertson, and I'm part of the SimuFact business development group. And so, let me see, just going to go ahead and scroll to the next slide. So we have, like I said, additive manufacturing or advanced simulation to leverage additive manufacturing potential. A little bit of background first, just a broader vision of MSC for additive manufacturing and component design and finite element analysis simulation as a whole. So we really take a holistic approach, being able to go all the way from the very low, very small micro end of materials modeling up through the fabrication and then testing of the components themselves, the assembly of components into systems, and then testing of systems. So it's really an end-to-end solution that can incorporate every aspect of the process from the very, very small to the very, very large. Part of MSC is part of Hexagon Manufacturing Intelligence. And so we understand that the comprehensive AM workflow is not just building a part, it's not just designing a part, it's not just testing a part, but it's several steps that have to be taken consecutively and as well with iterations, including developing the part, the topology optimization, selecting the right materials and machines, having that printed, the part, the first time right, as it's called, also being able to then consecutively or consistently print those parts or build those parts to be able to achieve quality parts over time, and then also being able to measure accurately and consistently measure and then track the data that goes along with that. To be able to validate that it's the as designed is truly as it's being built. And in the center of the wheel, you can see all of this is tied together with a material data management process. It's very important. So within Hexagon, the intent is really to combine all these best manufacturing technologies, and really the simulation aspect fits in to this loop. As part of this process, you start with CAD, but then go through the engineering, design, development, simulation onto the manufacturing process, which is covered by some of the other products that are offered by Hexagon, through the validation, and then ultimately as well through the controls, statistical analysis, etc. Very brief background about SIMUFACT itself. So SIMUFACT is short for simulating manufacturing. It's really, we focus on the manufacturing process simulation for metal manufacturing processes, including metal forming, welding, and additive manufacturing, specifically focusing on powder bed fusion at this point in time. Development is still done primarily out of Hamburg, Germany. Olivier, if you'd like to give a background maybe on e-xstream.
Hi, this is Olivier from e-Xstream Engineering. I'm the business development engineer for Additive Manufacturing. So e-Xstream Engineering, we are the material modeling company, about 60 people, essentially PhDs, all very focused on advanced material modeling. Our headquarters are based in Belgium and Luxembourg. We are developing Digimat, which is a platform made of different tools and solutions to model plastics and composite materials. We are the global market leader in multiscale modeling, with a very broad market leader in automotive. We're working with most of the material suppliers on the market, and we're part, of course, of MSC Software and now of Hexagon.
Thank you. Now you might see a short buffering. I'm actually going to go ahead and start sharing my screen. So just bear with me. And we're going to get into the next portion of this discussion, which is focusing on SIMUFACT Additive. So this next screen update, some of the main challenges associated with metal powder bed. Let me see. Did I lose my screen share? I think I did. Try it again. Main challenges associated with metal powder bed additive manufacturing are related to residual stress and strain. So the process of metal additive manufacturing results in a significant amount of residual stress and strain just imparted by the thermal effects of what is essentially a very small micro welding process. So this results in a lack of dimensional control, parts that can crack, separate from the base plate, delamination, as well as collision with the recoater blade, and numerous other sorts of phenomenon that are generally not desirable. This associated with the quality and productivity and the demands to try to achieve qualification, and the fact that these parts typically cost from $2,000 to $20,000, and to date it really required iteratively to trial and error this. This is really what drove the need for simulation to really move the industry forward. So some key considerations within additive manufacturing process simulation, there's a couple of important aspects that I wanted to highlight here today that are specifically as it pertains to SIMUFACT Additive. The first is that SIMUFACT Additive covers a comprehensive AM process chain simulation, in that we go through more than just the build, and I'll get into that in more detail. Secondly, being ease of use, learning curve, and modeling time. Then followed by the calibration of the simulation to a physical build, or empirical, based on empirical data. That, with the fact that it's a very quick, very fast, and robust solution. And finally, one of the more recent developments, the capability to utilize an automated iterative compensation routine to get your parts to the final desired geometry, compensated geometry very quickly. So first off, we want to talk a bit about considering the complete AM process chain. So we understand that the AM process is comprised of a number of different steps, and that we can model several of these numerically. So not just considering the build, but also the unbolting or unclamping, the heat treatment, the cutting of the base plate supports, subsequent heat treatment and HIP steps, and then also the process that occurs after that. All these things can have a significant influence on the final part shape, and considering the build without post-processing is really only part of the picture. Oftentimes I say, I don't know a whole lot of parts that are very useful while they're still attached to the build plate. So first off, considering the comprehensive AM process chain, as I mentioned, build followed by the unbolting, stress relief, cutting, support removal, and as well as additional heat treat processes. It's important to note that the base plate is deformable. What you can see here is a very realistic representation of a part. It's a real part, 225 millimeter shrouded impeller made out of titanium on a 40 millimeter base plate. And you're going to see that when you unbolt this after build, that base plate deflects upwards of 5 millimeters. This is a real phenomenon, and it's been validated by folks who actually built these parts. Secondly, being the fact that you can't neglect or ignore the heat treat process. Parts change shape as a result of this heat treat. They expand as you start to heat treat them, and after cooling, they're not always fully annealed. Also, the parts change shape. By the time they expand and then contract back down, they're not necessarily the same shape. This also is affected by the fact that if you have a different material for the base plate versus the powder, in an example here, a realistic example based on our practical experience with customers, a 1045 base plate with an Inconel 718 powder. This also enables us to optimize the heat treat schedule. So here you can see an animation of the part going through a heat treatment, the stress relief that's taking place. Then as it cools down, you'll actually see that there's a small, a stress that propagates at the base plate. And this is a result of the delta between the thermal expansion coefficient of the 1045 and of the Inconel. Finally, the cutting and support removal. Especially important when you're actually cutting prior to the stress relief, this can result in a significant deformation, depending on how you cut the part. If you cut it left to right, right to left, front to back, or some other way, it can affect the final deformation. You'll have localized plastification that's different depending on the direction of cut. This is also especially important for hybrid additive manufacturing machining applications that are starting to become much more prevalent. Next, we wanted to talk briefly about the ease of use and modeling time. So our standpoint is that the ease of use and the ability to use this solution very quickly and effectively, not requiring to be a specialist in CAE, having a PhD in computational methods, and also not having to go through and de-feature the geometry or clean up or do these other tasks. It's going to really enable this technology and also accelerate the modeling process. In this case, we routinely see that we can model a process in 5 to 15 minutes. Also a short learning curve. Basic training is usually a WebEx with me for about an hour and a half. And then an advanced training beyond that is another 8 hours, give or take. Some people never get it, and some people do, either by WebEx or in person. But this really enables us to get users up to speed very quickly and also supports the democratization of the simulation capability. It makes it so that people who are very close to the machine, somebody who, again, has no experience with CAE, can readily utilize the tool. Now, I wanted to show you a very brief animation. It's about 2 minutes long, but it's going to show you that the modeling process can be completed in about 2 minutes. So we're going to go ahead and you can see that we're going to go and they're starting with a brand new process, changing the name of the process, changing some of the setup parameters, changing the machine, importing the part. And the part you can utilize pretty much any kind of format to import the part. You can the next step would be to position the part, and then they would go ahead and import the supports, or we could generate the supports organically within the software. Again, it doesn't matter whether you're using your own supports generated in Materialize, or generating the supports within Simufact. We can also, like I said, consider the deflection, the thickness of the base plate. Here we're selecting the powder. The next step is to apply the build parameters, the cutting parameters, and the support removal parameters. Next step would be to create the voxel mesh, or the finite element mesh. In this case, we're using about a 1.5 millimeter voxel mesh. This takes between 10 seconds and 30 seconds typically. And then once we have the voxel mesh, you can go ahead and kick off the run. We'll talk a little bit about the solve time here after that. You can see a little bit of the detail of the voxel mesh that's applied. It's important to note that we are able to utilize a voxel mesh that is relatively large by comparison. And some of the approaches that we take from a numerical standpoint that allows us to utilize a larger mesh, which also supports us being able to solve these models very quickly. All right, I'm going to go ahead and so the next thing I wanted to discuss was calibrating the simulation to a physical build based on empirical data. Now you might hear, oh, well, I have to create these coupons, and that can be a pain. But in reality, the way we view it is that simulation based exclusively on a numerical analytical approach really cannot capture the inherent variability of the process. And so some sort of way to ground it in reality is critical. So with a typical AM process machine, you've got 180 plus adjustments, and then the machines change over time. So like I said, the analytical approach will not be able to consider the machine-specific performance without an extensive calibration. And this is why we prefer to take this physical test-based calibration. It's the fastest, most accurate method to calibrate the simulation. And it really does consider everything that occurs within the build chamber. We validated this to upwards of 95% accuracy in blind studies with industry partners, companies that you have heard of. Simple process of building, measuring, cutting, and measuring again. It considers the micro variability that's inherent in this process, that's inherent in AM, and one of the things that makes it very difficult. So simulation itself, as I mentioned, you can't do it purely based on numerical build parameters, purely analytical methods. So the question is, two identical machines, or in this case, GE, 150 machines, same recipe, same powder, same build file, same STL. Do we get the same part? And the answer is not necessarily. What about the same part, recipe, combination on two different machines in two different locations, an EOS and SLM? What about an EOS in the US, SLM in Europe? Will you get the same part then? Probably not. But this empirical calibration is what enables us to build the same part across multiple machines and locations. Want to also discuss the speed and robustness of the solution, capable of solving very large realistic models. And I say very large, what is that? So something that would occupy the entire build space of an M400, an STL greater than a gigabyte with 1 millimeter size features, can be able to handle that kind of a very large part. This simulation will solve routinely without crashing. It's very robust in that respect, and quickly solve realistic part level simulations. So a lot of times we'll see a simulation and say, oh, well, how long did that take for that 1 centimeter, 2 centimeter part? Well, in this case, we're talking small to medium parts, maybe 100, 200 millimeters, solving in 15 minutes to an hour, including the build, heat treat, cutting, support removal. Large models, most of a 250 millimeter build space, 4 to 24 hours. Small to medium models only require a laptop or a moderate small CAE workstation. I solve all my models on a 4-core 32 GB RAM laptop. It works just fine. You get into some very large things, extra large models, 64 to 128 GB. Also capable of solving on Linux cluster. Here you can see an example. Again, I ran this on my laptop, 260 millimeter Inconel turbine blade, the same model we saw earlier. Build, heat treat, base plate, cutting, support removal. 1 hour, 24 minutes. Last topic I wanted to discuss is automated iterative compensation routine. So in this, it's my personal opinion that the compensation is going to become something that is critical and an enabling task or enabling capability that's going to bring metal AM forward. I kind of make it's analogous to the compensation of castings. And so we're able to predict that optimal shape, and in doing so, we want to build the part to nominal, not try to build the nominal geometry, as we've been doing pretty much up to this point. Some areas within the geometry may require more or less, and this is what drives the need for an iterative compensation, something that's more than just a one step. And so SimiFact, in its latest release, has developed this capability and this automated routine that's starting with the baseline results here, you can see, then to the compensated results. And so I'm showing you on the top, I'll just go back to the last image. So the baseline here, you can see the top image being the initial displacement, but then the bottom image is the shape deviation, and that's really applying a best fit because there may have been some rigid body motion or some other change in the shape that's reflected in the total displacement. You see it's about a 1.09 millimeter. And then with the compensation, and this only took, I ran this last night, it only took one iteration. I was hoping it would take more steps than that, and it got down below the threshold that I applied. So basically the process that it goes through, you specify the max number of deviation, or the max deviation, and this is a screenshot out of the software. You say, I want it to be, my max value is plus or minus a half a millimeter in this case. I'll run a maximum of 10 steps, and then it will automatically run that simulation, measure the deviation, compensate the geometry, rebuild the model, rerun the simulation, and on and on and on until it gets to that point that it's successful or it reaches your maximum number of steps. And in so doing, you're able to achieve your optimal compensation with minimal user interaction. So at this point, I'd like to turn it back over to Olivier, and I will go ahead and push it back. Olivier?
Thank you, Jeff. So we all know that manufacturing transforms the material and influences the final part performance. And so what we've been doing at Digimat for 15 years now is really connecting the manufacturing process with the part performance, and we do that via the material behavior and microstructure. So Digimat is a material modeling platform to support industry composite-related needs and pains. So you can have access to virtual testing, so to deduce the composite material behavior based on the different phase material properties. You can have any type of question as a what if I change the volume fraction of the fibers, the volume fraction of the porosity, how will it impact the mechanical or thermal behavior of the composite materials. We rely on a very large material database, Digimat MX. We're working with most of the material suppliers to build material models, to exchange them between material suppliers and end users. We have different types of mapping solutions to transfer information from mesh A, from process simulation, for instance, to a mesh B, so the CAE mesh. And then we are interfaced with most of the FEA solvers on the market, so MSC software solvers, of course, like Mark or Nastron, but also third-party like ANSYS, Abacus, or SAMSEF. And finally, we have also developed 2 years ago a process simulation module, Digimat AM, to deduce the level of warpage and residual stresses of the part. So our solution is based on 3 different building blocks. We have material engineering, process simulation, and part performance, because of course there is a very strong link between each of these building blocks, and specifically for additive manufacturing, materials will play a very important role. So the aim of material engineering is essentially to predict the mechanical, but also thermal or electric material properties, because we are more and more heading towards multifunctional parts with additive manufacturing. Process simulation for FDM or SLS processes is aimed at predicting warpage, residual stresses, but also some information about the as-printed microstructure, such as porosity or the type of related microstructure effects, such as crystallinity. And finally, by combining material engineering with process simulation, we can replicate the successful workflow and predict the end part performance, so it's stiffness, but also failure, and failure is often print direction or reinforcement dependent. So for materials, high-level kind of application that you can perform with Digimat. First, you can develop virtually some different types of composite materials, so high-performance materials. So let's imagine that you have a PEC filament. You can envision to reinforce it with carbon fibers. So you can investigate directly the effect of adding carbon fibers. This is the red curve that we have here. And then also, again, answer typical what-if question. And what is, if I have 1% of porosity, how does it impact the overall material performance, for instance? We have developed very advanced material models for injection molding, but also for additive manufacturing, where we account for the specific and complex microstructure resulting from the process, the additive process. We have built up a mechanical behavior of lattice microstructures, and we also are investigating multi-materials, such as a Stratasys polyjet, where we can directly deduce the overall stiffness of the material, depending on the volume fraction that you have between a very low material and a very stiff one. Process simulation really aims, again, at predicting warpage and residual stresses. We have a solution for FFF or FDM and SLS. So what we do is that we account for most of the process settings occurring during the simulation. So it can be the toolpath that is illustrated here for FFF or FDM. We account for the chamber temperature, for the laser beam in SLS, and so on, but also of all the different material properties. And based on all the different input, we will then predict the warpage of the part and its assembly layer by layer. Then we will end up with the first prediction of the warpage of the part as it is printed in red here. And similar to Simufact, we offer some compensation of the warpage capabilities that allows you then to change the geometry to print and finally achieve the right level of accuracy that you might want. So in terms of performance, this is essentially about replicating the successful workflow that we developed for injection molding 15 years ago. So at the bottom, you have the connection between the manufacturing process simulations done with MoldFlow or Moldex. And from these type of simulation, we infer the as-manufactured material microstructure, such as the fibrous orientation, for instance. And again, combining that information about the material microstructure with its material characterization, we are then capable to predict the final part performance. So this is the same workflow essentially that we want to replicate now for additive manufacturing with the example in FDM at the top now. So we have developed all solutions for process simulation because simply it was not existing on the market, and combining these with specific multiscale methodologies to describe the material microstructure, its behavior, and finally predict the part performance. So e-Xstream offers a unique database. So for injection molding, compression molding, and other type of processes, we are working really with most of the material suppliers. But for additive manufacturing specifically, we've been working with Solvay and Stratasys to develop some material models of different grades in FFF, like we do with Solvay Cetaspire. So this is a peak material. But with, in FDM with Stratasys, we've been working at characterizing the ULTEM 9085 that has been certified for aerospace, and also on the 1010, which is more dedicated to toolings. And with Solvay, we've also been working on the Sinterine grade for SLS process. Finally, we've been capable to characterize the Fortus 900, which is probably the largest FDM build size on the market, and that has a specific package for aerospace certification. In the near future, by the end of the year, we will have additional grades coming from Solvay, Stratasys, and probably also more material suppliers, and some of them will then be loaded with carbon fibers or glass fibers. So when we released our first Digimat version, we had a solution based on the in-on-strain approach. So this is very similar to what is proposing Simufact. So it's proposing essentially a very good compromise between accuracy and speed, and is essentially answering the question on will my build print right the first time? So what is the overall warpage trend, etc. Now, with the latest release in July, we've enabled advanced solver simulation, which means that then you can now perform a full simulation, thermal analysis or thermomechanical, and taking into account all the different local features. Okay? For that, for instance, we can have a very detailed, so separate very local detailed thermal impact of specific areas, have some specific toolpaths like lattices, for instance, or predict the level of crystallinity in the part. So this is really the type of study that are ideal to first understand and then optimize the process, for instance, with the degree of crystallinity in the part before printing physically the part. Now I will switch and end with an application case from Solvay Engineering Plastics. So this is the SLS process. It's a Sinterine grade, so it's a PS6 with 40% of glass beads. And essentially, as you can see in the workflow illustrated here, the idea is to integrate simulation really at the heart of this physical printing workflow, and first predict and optimize the part performance, predict and compensate warpage, and then in the end evaluate the impact of the building direction on the part. The part in question is coming from the industry. It's an automotive engine part, and it has to sustain a given amount of pressure at a given temperature. The first step for this is to characterize the material behavior, and to this end we perform some tensile and compression tests that will give you the different results on the left tensile and on the right compression. And we do that at different building angles. So this is the Z, the vertical direction. So these are the different layers within your build. This dumbbell here at the bottom is printed flat, and the other one at 90 degrees is printed vertically. So what we do is we characterize experimentally the mechanical behavior. We fit a Digimat model through the different curves, and what we can see is that essentially the building orientation doesn't really impact the stress-strain shape. But it does have an impact, and this is on the failure, so that the failure happens at very different values depending on the building direction. And so this is why we had to develop a new specific failure indicator that is aware essentially of the building direction. To develop this failure indicator, we will reuse the different dumbbells printed and tested at different orientations, and we will then show that indeed we are capable, compared to the experimental curve in blue, to fit a Digimat model of the failure, and indeed we are decreasing progressively the maximum strength of the material with an angle that is increasing. So the worst condition, of course, in this case is when you print the dumbbell vertically. Now that we have characterized the mechanical behavior of the material, we can perform structural analysis to deduce which orientation of the part is giving us the optimized performance. So in this case, it's the burst pressure, so we have to sustain the maximum level of pressure that we can, and to this end, we will see this animation that gives us the evolution of the maximum pressure that the part can sustain in function of the building angle. So from these results, we see that there is clearly a preferential angle at 0 degree or 180 degree by symmetry. Now what we have to do is to check that the design accuracy will be satisfied during the printing. So this is where printing simulation occurs, of course. For that, we will print the parts at the two different orientations, 0 degree on the left. So this is the animation that is played now, and 180 degree just afterwards on the right. There is one specific area of the part that we want to investigate, and this is the sealing area at the very bottom of the part. And so when we print it at 0 degree, we can see that there is some warpage, as demonstrated experimentally on the right slide. So this is the famous banana shape that we have when we print a plate within the build. While when we print it at 180 degrees, essentially the first build is already correct. So we'll then use Digimat AM to perform the process simulation and use those first results to compensate the warpage. And so on the right now you can see the updated results at 0 degree, where we have decreased most of the warpage that was existing on the first build. I will now switch to Material Center. Material Center is essentially a tool that has been developed to address a given number of pains when we discuss material testing with a company. The first, material testing is very expensive and it's also labor intensive. The approval process is often manually, poorly tracked, and the use of unapproved materials across the company can result in unreliable or unrepeatable results. So all in all, about traceability, about linking all the people together, we want to offer to the market a material data and process management solution. So for that, we will first start by loading some data. So it can be physical test data, of course, like tensile tests, but it can be specifically for additive manufacturing as well, process data or material parameters. This means that you can really follow up and include all the different data that are associated to the full simulation and the full additive manufacturing process. You can also envision to include some virtual data with Digimat, so the connection with Digimat VA. Once this is done, you can analyze, post-process, and reduce all the data, and all this is sustained by a very specific approval process, meaning that this is really an integrated platform within the company. Once the data has been approved, we can also start using them. So this is about exporting the data to Excel files. So we have an Excel integration within the tool so that engineers can work directly from the Excel interface, download the data, modify them, publish them, and also create some specific templates. You can also export the material data for CAD, like CATIA, or for CAE, like MSC Software, Patron, NARC, but also Abacus or ANSYS. And finally, you can publish the data towards a PLM interface, or just creating reports and emailing the information. Finally, and last but not least, we have a compliance solution. So in partnership with iPoint, we want to be capable to produce data that are REACH compliant. So specifically for additive manufacturing, it will Material Center will enable you to capture the full AM data, so about the material, about the build, the process, the machine, even the environment of the part, in one unique centralized platform. Okay? So you can capture the full manufacturing process and ensure then consistency and provide also quality indicators. You can also compare with virtual data or with different scanning devices data. And finally, you can also provide AM and non-AM data sets for process benchmarking and comparison. This workflow has been successfully applied with the US Army. And so essentially, their need here is really to optimize the additive manufacturing parameters to produce reliable, field-worthy components. And to do that, they wanted to essentially have traceability. So they want to make sure that they are tracking for each build the machine information, the material that they've been using, the properties, and so on. So that afterwards they can review all this data, compare them, analyze the trends, and finally optimize the machine parameters to produce consistent and reliable components. And moreover, different kind of templates have been developed specifically for powder bed fusion, for direct laser deposition, and so on. And so the value that they've found here is really to be capable to quickly search across a huge amount of data and different types of batches to find the optimal material properties, details on one specific build, part that has been built, so traceability again, or simply trends in the data, and finally to have more predictable builds to produce simply consistent and reliable components. So this is the last slide of these presentations, so I would like to thank you for your attention. I think that we will now switch to the Q&A session.
Thank you, Olivier and Jeff, for that insightful look at using advanced simulation to leverage true additive manufacturing potential. We've received several questions from the audience, and we'll begin addressing them now. And if anybody else on the webinar comes up with any questions, feel free to enter them. We'll now be able to stretch a bit beyond the top of the hour if need be, and you're welcome to stay with us. But if you can't, remember that you can revisit this webinar anytime you wish after 4 p.m. Eastern Time today. So on to our first question. Do you consider all the process parameters while doing warpage and residual stresses analysis?
My question in response to that is that for the metals or polymers or both? I guess. And so from the standpoint...
You know, if you could touch base on both, that would be great.
Sure. So from the metal side, I can speak to that. Initially, we are able to utilize multiple approaches within SIMUFACT additive for metals, metal powder bed. So we can consider the process parameters taking a more traditional multi-physics, thermomechanical, coupled finite element analysis approach. And in that case, it would consider the laser power, scan speed, hatch strategy, recoat time, etc. But then within the inherent strain approach, as I described in this presentation, where we utilize the calibrations, within the calibration themselves, all of the everything that's within that build, all that recipe is baked into the build. It's baked into the to those calibration beams, and we see that it's really quite accurate and surprisingly so. I hate to say it that way, but surprisingly so. It's very accurate and very fast. Like I said, we've seen in terms of distortion, 95% accuracy when comparing. And so hope that answers your question. Feel free to reach out if you have others.
From the polymers and composite side, the methodology that we use essentially relying on the multiscale methodology. And so during the process simulation, indeed, we do account of several process parameters. We also account for the material properties, such as the Young modulus and the CTE and so on. For process data, it will depend on the process we're discussing. For FDM, we will include, like I mentioned, upload the tool path and take it into account. We will also account for the printer head speed, for the bead width and layer 8 and so on. For SLS, we also account for the powder characteristics, so the laser characteristics like its power, the laser beam, and so on.
Thank you. Now on to our next question. Is it possible to know what happened if we feed the compensated geometry back into the simulation? Did it yield almost no distortion?
So that was actually what was displayed at the end of at the second portion of that slide. So initially, I showed the first portion of it. I showed the initial distortion, total distortion. It was just a couple of looks at the distortion, and then the shape deviation. And I think we're switching to that slide here. So on that right side, those are the baseline results, and then the next results would be actually the compensated shape. And so what it does is it automatically runs that until it gets to that iteration. So this is what would happen in the simulation if you ran it back through, because that's how it does it. It runs it back through.
Okay, thank you. And also another question is, what format is required for CAD and supports?
So from the SIMUFACT additive standpoint, we are totally agnostic, can take pretty much any kind of format as far as I'm aware. So whether you're utilizing an STL or an STP as a generic file format, or whether you're using a SolidWorks file or a Creo file or anything else in between, we pretty much take all of them.
Great. Now we have another question. Is the SIMUFACT FE approach technical content available to share?
I'm not sure I understand the question, I guess. I would probably want to touch base with you offline to make sure I understand. I'd be glad to share some of the technical content.
Okay. Is there any place online that the attendees can go to find more information about that, or is it better just to touch base with you?
I would recommend just touching base with me. You know, there's a lot of material online. You can certainly go to our website, but at the same time, you know, if you're looking for something specific, I'd be glad to interact directly.
Okay, that sounds good. And we have another question here from somebody in Germany. Do you support simulation of deformation caused by sintering at MBJ processes?
I am not familiar with MBJ, so I can't say.
Okay.
Multi-binder or metal binder jetting. Oh, so like the new HP metal binder jet process, I'm assuming. We're looking into that. It's not commercially available yet. I don't know, maybe Olivier, could you speak to metal binder jetting from a Digimat side?
So yeah, I think this is a metal. So we do not support it. It's on your side. Yeah, we do support SLS and FDM. More processes will come, but for the moment, these are the ones that we support. At least from the process simulation side, for part performance, we can always have a look into it and characterize the material.
Okay, thank you, Olivier. And here's our last question. How can I speak with one of you about an upcoming project that we have?
I would just say to email me directly would be the best way. Or we can also reach out to you after this email if we have your proper contact info. Okay,
perfect. So as this webinar has shown, there are many opportunities and benefits when MSC software helps manufacturers advance and customize simulation techniques to optimize the design, the print workflow, and determine the optimal process flow at a faster and lower cost. SME and SME Media can help you keep abreast of developments in additive manufacturing. At www.advancedmanufacturing.org, you can read about how the aerospace and defense industries see 3D printing as vital and how the Service Bureau is investigating an advanced 3D printing technology. And always keep an eye out for breaking news coverage of 3D printing on our website at advancedmanufacturing.org. In addition, SME features the latest manufacturing technologies at events including AMT's MT Forecast Conference, formerly known as Global Forecasting and Marketing Conference, October 10th through 12th in Indianapolis. Thanks for joining us for this SME Media webinar. We hope you found it informative.